1.2 Number sets and subsets. So a set is a collection of elements of any kind. Okay, it could be objects, symbols, numbers, points in space, lines, geometric shapes, variables, and a set of anything. Okay, and what we do is we usually draw a circle and we put in like a bunch of the items. For example, like this would be objects, and we just call this a set. Okay, it's just like a group of items that all have like the same theme. Okay, and when we talk about subset, we say that like A is a subset of B if what happens is every element A is also in B. So this is our example. Given A is 1, 2, 4, so see how like A is here, 1, 2, 4, it has these three numbers in it. Oh, this is supposed to be B, and B is 1, 2, 3, 4, 5. So if you can see B is like the bigger circle, and it encases the entire A. So all of A is in this, 1, 2, and 4. And then in addition to that, we also have 3 and 5. Okay, so what is the relationship between these sets? We can say A here is a subset of B. Okay, element. An element of member is a member of a set in any one of the distinct objects that belongs to the set. Okay, for example, if we had the set A, 1, 2, 3, 4, what this means is that the elements of set A are 1, 2, 3, and 4. Okay, so there's 4 elements in A. Okay. And the last one, Venn diagram, and we're going to take a look at Venn diagrams. So a Venn diagram is an illustration that uses circles to show relationships amongst things, okay, or finite groups of things. So this is an example here. We have two circles. Let me make my pen a little thicker. Okay, we have 2 circles here, and if we take a look at the circles, we're talking about banana in one circle and lemon in the other circle. So bananas are smooth and sweet, but they're also yellow and fruit, and lemons are also yellow and fruit. So because those two share these qualities, yellow and fruit, we put those in that overlap. Okay, and then lemon is sour and bumpy. So that's how we draw a Venn diagram and how we read it. Okay, example 1. Given x equals ARE and y equals READ, organize the elements into a Venn diagram, then state the relationship between these sets. Okay, so we're going to label this first circle X, and we're going to write in it all of the elements in X. We're going to name this circle Y, and we're going to name, list in it all of the elements of Y. So let's take a look first at what is in this. It's called intersection, or like what's in that overlap. So A and A, so A will be in the overlap because X and Y both have an A in it. R and R is going to be in the overlap. And E is also going to be in the overlap. Okay, nothing in X is not also in Y. So the X only, like right here, this is going to represent X only, and there's not going to be anything in it. The only elements in X are A, R, E, and they're also in Y. Okay. However, the one element in Y that's not in X is D, so we can put that there. Okay, if we're actually thinking about this, we could also draw a big circle to represent Y and a smaller circle to represent X, and we could write D-A-R-E. And the reason why we can do it this way, which is not as common as drawing a Venn diagram like the first way, is because X every single element in X is also in Y. So X is a complete subset of Y. So we can say X is a subset of Y. Example 2, given P equals 1, 3, 4, and Q equals 2, 3, 4, 5, 6, organize the elements into a Venn diagram, then state the relationship between these sets. So I'm going to name this one P and this one Q. First, we want to take a look at the overlap. So 1, 3, 4. Okay, we have 3, 4 in both of these. So we're going to label 3 and 4 in the overlap. What's unique to P is the number 1, and what's unique to Q is 2, 5, and 6. So we can say P, the notation is like and, P and Q share. So this means like share 3 and 4. And we can leave that as the relationship. Okay, and example 3. Given A is 1, 2, 3, 4, 5, and B is 3, 1, 2, 5, 4, organize the elements into a Venn diagram, then state the relationship. So let's look at what overlaps. So let's call this A and this B. So 1 overlaps, 2 overlaps, 3 overlaps, 4 overlaps, and 5 overlaps. So 1, 2, 3, 4, 5. Okay, so if we actually take a look at this, there are no elements that are unique to A. That's going to be empty. There are no elements that are unique to B. So we can say like A equals B. They both have the exact same elements, so A equals B. Okay, now we're going to take a look at number sets. Okay, so we take a look at sets in like real life, maybe shapes or numbers, okay, and that's like a really popular application. Now we're going to take a look at the actual number systems, okay? So we have different number systems that are called different things and they involve different numbers. So we have one called the natural number set. The notation used for this is an N, and if you notice here on the N, it's a double bar. Okay, and you can notice that for all of these, like the double bar. For R, it would be like the double bar here and then an R. Okay, a little bit different on the computer than when we write it, but that's okay. So the natural number set, when we talk about natural numbers, we are talking about starting at 1 and increasing integers. So they're specifically positive integer values. Okay, and in this diagram, we can see the natural numbers are a complete subset of every other number system. This is the smallest number system that we refer to. Then we have the whole number system. Again, the W is double W like this. Okay, what the whole number system is it's all of the natural numbers, and then it expands to 0. So see how that one also includes a 0? So we'd start at 0 and we'd increase by only integer values. No decimals, no fractions. Okay, 1, 2, 3, 4, 5, and we'd keep going. The dot, dot, dot implies that we go to infinity, which is the biggest number. Okay, it just means we go forever. Now, the integer number set is positive and negative integers. So when we denote this, it's with a Z, with like a double bar again, okay? And the integers have all of the negative numbers as well. So we would put dot, 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 because it goes to negative infinity forever. Okay, and then it's like, say, -10, -9, -8, all the way, -2, -1, 0. Then it flips over right here to positive numbers, 1, 2, 3, all the way up to infinity. Okay, so these are called the integers. The integers include these negative numbers as well. Integers include the whole number set. Integers also include the natural number set. Okay, the rational number set. This is a Q with a bar through it. Okay, this is specifically fractions. These are numbers. These also include numbers that can be expressed with like an integer over an integer. So P over Q. Okay, so now we have all of the normal numbers like 1, 2, 3. They're called natural numbers. We have whole numbers, which include the 0. We have integers, and now we expand to rational numbers. So that includes the fractions. However, there are certain numbers that cannot be expressed as a fraction, and what we call these is the real number set. So, for example, if you put √3 into your calculator, you would get like the number like 1.732 and so on forever and ever. Okay? That number cannot be, like √3 cannot be expressed as a fraction. It's specifically a root, and it's a really ugly number. So the real number system includes any other number that we haven't even talked about. So real numbers touch on every number ever existed and existing for every decimal place that you can think of. Okay, E is another number. E is 2.17. 2.71. 71828 goes on forever. And then pi, if you have, like we usually round pi to 3.14, but in this case it's 3.141592 and so on. Okay, and all of these are going to be part of this real number system. Outside of the real number system, we won't talk about probably for right now for the scope of the curriculum. So we're always going to be talking about numbers within the real number system. Okay, practice 1, state the number of elements or members in each set. So cow, pig, chicken, dog. We have 4. Okay, there are 4 elements. On your papers, there should be commas. 1, 2, 9, 11, 45, 66, 100. 1, 2, 3, 4, 5, 6, 7. So here there are 7 elements. Okay, practice 2. Match each parent set on the left with its corresponding subset on the right. So if the full set is 1, 2, 3, 4, well, we can't have negatives in that. So the subset of this will be 2. So number 2, Roman numeral. Okay, B, -5, -3, -1, 1, 3, 5. So if we take a look at what's left over, number 1 doesn't have 5s in. Sorry, I'm looking at it the opposite way. This subset has a 4 in it, but B doesn't have a 4 in it. So it's not this one. It's definitely 3. Okay, so 3. Now C, -4, -3, -2, -1. Okay, that's definitely number 1. It has -4 and -2 in it. So we just matched like the parent set to the subset. Okay, practice 3. List all subsets of 1, 2, 3. So we could have a subset 1, a subset 2, and a subset 3. And those are all of the different subsets with 1 element in them. Then we could have 1, 2, we could have 1, 3, and we could have 2, 3. And those are all of the subsets that have 2 elements in them. 1, 2, 1, 3, 2, 3. Yep. So there are 6. Here's another subset. We could have something called the null subset. This is called the null subset, and this is the empty subset. Okay, and I'm going to interpret this that we don't list off the subset like 1, 2, 3, because then those would be equivalent. So I'm going to leave it at that. Now, practice 4. Fill in the blanks with number sets. Okay, the set Q, so if we go back to our number sets, what number set is Q? This is the rational. And this means that it's like A over B, right? This is only a subset of the real number system. Whereas the whole number system, which is 0, 1, 2, all the way up, is a subset of the integers. So there's integers, Q, which is the rational ones, and then R, which is the real number system. So when we talk about something being a subset, we're saying, like, what does that one sit inside of? Okay, what's bigger than that, but includes that?